Alright, welcome back. So today I wanted to try and work on a new project, and I decided to stream it because it's probably easier even for you to give feedback, real time. And I want to try and start working on this stenography project. It's pretty hard to pronounce it, so we're gonna just call it Stego. And basically, what do I want to do with this project is to have a CLI tool. And for the start, let's just say that, well, we are going to have an image, we are going to have some hidden message that we want to hide in that image. Maybe we want to hide another thing like another image inside of our image. And here on Wikipedia it gives a bunch of other examples, but ideally, it's gonna be a byte string that we are gonna try to hide in our image. So yeah, and we're gonna start, from scratch in C, and we'll start with the easiest method first, which is just modifying the bytes, like the pixels of the image, to encode our hidden message, and then we'll try to figure out better methods. I'm not sure if it's shown here, but um, I did something like this in the past. Well, it was like a CTF challenge, and you had to search for information, and I know that you can use things like Fourier transforms and more complicated things like that. Um, so yeah, but it's not gonna necessarily make images that are gonna be I know there are stego tools that can find hidden data. I'm not sure if it's gonna work with those, so we're gonna have both the encoding and the decoding part done in our CLI tool. So as usual, we'll create the okay, don't mind what the fish suggests. We are gonna create new project. I think I'm gonna call it Stegatron. It's like Stego and Megatron combined. It's really weird. I asked ChatGPT about it, so he said call it Stegatron. So we're gonna create this thing, and yeah, maybe you noticed that the aids.h library, I decided to change from ds.h and call it all-in-one data structures because it makes for a better name, I guess. I'm not sure if we are going to use this thing because it's probably not going to be needed to have data structures yet. I'm going to go for, the simplest way of working with C, which is just pointers and numbers. So I guess we are just going to try to do that for starters. Okay, so let's start by copy pasting this flake though, because that's something pretty hard to do. Techniques. I mean, basically this thing is just going to install Clang and Valgrind for us, so I'm just gonna run it until it's done. Hello. And I'm curious how I can maybe put that thing on another monitor, but yeah, whatever. Okay, so we have the Clang thing. Okay, perfect. So I guess we are just gonna have a single main file. Okay, my instincts, right? It's gonna be main.c. Oops. Anyway, so the idea is now we have Clang. We can just compile it, but let's start with include the usual stdio.h int main, and let's printf hello world. Okay, and maybe return 0. So let's run it. We get some hello world, perfect. And some other tools that we are gonna need, some other libraries. I'm pretty sure we're gonna need a stb image, right? And I want to be able to load images and save images, so I'm probably gonna use stb image and stb image write, and I guess this one is a pretty cool repo for easy plug and play libraries. It has a bunch of other libraries as well. I think the one that I use the most from here is just stb image. I haven't really checked the other ones, but I see it has something like Perlin noise, sprintf. I mean, sprintf is pretty cool. It's implemented from scratch, but yeah, whatever. So we have this stuff. We can just get it. I think I already had that saved from the past. So, but let's just get these two. So get. So now we have both stb image and stb image write, so we can read and write images. That's perfect. Okay, another thing that we might need. No, pretty weird that they don't have it here. It's like a classic for stenography. It's the Lena image. Lena Wikipedia. Maybe we're gonna try to use this one. It's 512 by 512, so it's pretty small. Hopefully we are gonna run into some issues with that. So wait, can I just open the image in a new tab and get it? Hopefully it's, let me just rename it 500 into just lena.png. So we have this lena.png image. Does it look good? Okay, yeah, it's fine. So first of all, I mean, I'm gonna keep everything simple. Maybe just hard code the message from the code. Right, so let's see. Okay, so let's include stb image.h, and this library works similarly to how my ds.h works. So you need to define stb implementation for it to actually give you the implementation, so we have to do that. Honestly, I would put this first and then that, I think, just to make sure that it's not gonna interfere with it, but it should have something like stb image load, and it, I mean, in my opinion, it's pretty easy to use. It's just it gets the file name as a parameter, so we're gonna do lena.png. Obviously in the future we'll have like command line arguments, but for now it's not that important. And the other arguments are gonna be the image width, the image height, the number of components, so RGB is gonna be 3, and the number of required components, we are gonna leave it as 0 because it's like, doesn't matter. So let's do x, y, I guess components. I mean, usually I like to define them on separate lines. I don't know why. You had that in the past when I was doing like coding for school, I was putting everything in one line. I'm not sure why I changed that behavior, but yeah, whatever. So let's have the number of components, and maybe what we can do. Obviously we can check that data is not null. That's one thing we can do. And something that's nice in stb image, it has this stb failure reason function. Notice this one while I was implementing my own ace.h, and this one returns const char, And in case you get an error while maybe loading the image or doing something else, it gives you like a string with the error reason. So it's pretty nice. So we can maybe just do printf failed to load image, and then we just show that failure reason, and maybe we return 1. Okay, so that's how we get the image. Let's just printf maybe image loaded, and then we can say with %d it's number, height it's also %d, and components %d, and then we can xy comp. So if we are gonna clang and run this thing, we need, I guess, to add lm, because for some reason stb image uses math.h. So yeah, let's link with a math library. Fail to load image null. That's interesting. I thought it's called lena.png. Oh, if it's equal to null, I'm sorry, I'm stupid. Okay, so okay, we have an image of 500 by 500 and 3 colors. I mean, okay, so maybe this image is a bit bigger, so let's copy image link, let's get it, and we have this image. Let's move it into lena.png. So maybe now it's a bit larger, so let's see. Yeah, okay, I mean, it doesn't matter, it's the same thing. So yeah, we have this data, which is unsigned char pointer. Basically, we have 1 byte. I mean, each pixel is going to have 3 bytes because we have 3 components. So each of these things represent 1 byte of the pixel. So if a pixel is RGB, let's just add a comment. We have RGB. We have a bunch of these RGB bytes like chained together, right? So one after the other, we have RGB, RGB, and so on, right? And this entire thing is flattened, so its shape is basically x times y times components, right? So it's not really, you know, like a 2D array or something. We could make it a 2D array, but for the purpose of this thing, it doesn't really matter. Like, if you think about it, once you load the image, we are going to have a function that takes as an input a byte array and another byte array, and it tries to hide one byte array into the other byte array. So it's not even, you know, hiding data into images, it's just hiding data into data. So yeah, I mean, that's kind of the point. So we are going to have a function here. Yeah, I guess let's make it static. And this function is going to be our initial attempt of hiding some data. So basically this one, I guess the method that we are going to use is called least significant bit. So if you think about it, these RGB pixels are going to be values between 0 and 255, right? And obviously we could change these values, but the image is going to look different. And the question is, how different is it going to look if we change only one bit from this number, right? So imagine the color was I guess, what is a good example? Maybe 7, right? Maybe the value of R was 7. So what would happen if we just change the first bit, or I guess the least significant bit? Well, this thing will turn into a 6, and it's pretty much the same color, probably it's not even gonna be noticeable to our, eyesight. And although what I would like to explore, besides just changing the least significant bit, is how much of the image can we change while it's still gonna look kind of the same. So maybe we'll start with the least significant bit, and then we are gonna add the next bit as well, and third bit, and so on. Maybe we'll figure some cool stuff out. Maybe we can hide even bigger messages, because at this point, maybe if you think about it with LSB, what is gonna happen? Let's say we have RGB, RGB. What is gonna happen is we are gonna use 1 byte from this Lena image to hide 1 bit of information. So that means that we can hide 8 times less information in this image. So the image needs to be 8 times larger than our data. That's I guess that's the constraint maybe of this method of LSB, is that the data needs to be much smaller than the cover image. Okay, anyway, so let's have something like steg hide LSB. So this is going to be for the least significant bit, and we are going to have something like unsigned char pointer. Maybe it's going to be cover. Usually they call it cover in steg tools. We also need maybe unsigned, or I guess we can use size t for the cover length. Then we are gonna need also unsigned char pointer for the message. And let me just maybe I want to move this thing here. And also size t for the message length. Okay. So that's basically the first part. Okay, let's just call this function steg hide lsb, and we're gonna pass in our data. The data length, as I said, is gonna be okay, so let's do unsigned or size t data length. Actually, let's just rename it cover, because that's what it is. So we're gonna have cover length, and this thing is gonna be x times y times comp, right? So we have the cover, we have the cover length, and for the message and message length, we can just hard code this thing for now. So let's just say we're gonna have some kind of, I don't know, define message is gonna be hello from image, and message length. I mean, I don't think we have a way to get the length of a string directly. I guess it's size of, right? So if we do size of message, we actually get the length, right? Or am I being dumb? Let's check. So if I do printf, we have the message %s with size percentage, I guess %d. Okay, and we can put here message and message length. Okay, it's unsigned long, so lu. Okay, yeah, so we actually get the, I think it's 17, right? Yeah, it is 17, perfect. So we get this the length of the image. Although this one is 16, so I guess it also includes the null pointer. So if we do %lu and use %lu and we do string length on the message, it's gonna be simple. I would say 16. Yeah, okay, so we have to do -1. Doesn't matter. So here we get message and message length. So I mean, I guess that's pretty nice. If you have like a constant string, you can just do size of on that string and you get the length. Okay, what does it complain here? I mean, we can just const char pointer it. Unsigned, but it's also like a const. So this one is not gonna change. We can just make it const, and yeah. So that's kind of what we are doing here. And then we also have to save the image. So we have to use something from stb image write. So let's stb image write. And then I think this one is stb image write implementation. Let me just double check. So yeah, it is stb image write. And we can probably use something like stb I image or stb image. I think it was stb image write png. Yeah, so we can just call this function. So this one returns an integer. It gets the file name. So let's do lena out.png, and obviously we have already width, we have height, we have the number of components. Data is going to be still cover data, and the stride in bytes, I think this one is so when we look at this cover image, right, we saw that it's RGB, it's like an entire array of these RGBs. And what I think the stride in bytes means is how much you have to jump in this array to form a single line. So that should be width times the number of components, right? So it's the width times the number of components. That's when you jump to the next line. I think that's what this stb, this write meant. Okay, whatever. So we get this thing, and this thing might actually fail. So I guess it returns 1. I'm not sure, it returns 1 when it works. I guess it does, yeah. Or no, it returns 0 when it fails. Yeah, it returns 0 when it fails. That's kind of weird in my opinion, but whatever. So if this thing doesn't work, then we can just do something like this: fail to write image. And I mean, the reason why I say it's kind of weird to return 0 on failure is that usually 0 means success because you do return 0 at the end of the program. But yeah, whatever. So we have this lena out image. If we run this thing now, it shouldn't do anything because we don't do anything in hide image. So inside of lena.out, we should have the same image if I haven't done anything bad. Okay, so it's basically the same image. Can we somehow diff these two images? Image diff. Is there a thing like image diff? Pretty sure there, I mean, yeah, probably there is an image diff. But would it work with the diff tool? Okay, so it's not whatever. Maybe we are gonna implement a diff tool for steg, but we'll see. Okay, so what next? So let's try to hide this message in the least significant bit. Right, so first of all, we might want to do some checks. For instance, if the message length times 8, and 8 is gonna be maybe a define, byte size is 8, although byte size is gonna be always 8, whatever. So if this thing is greater than cover length, we are just going to return 1, which is going to mean failure, and maybe printf something like data is too big. I mean, we can fprintf to std error. Anyways, I'm gonna refactor most of these things later, but for now we are just gonna implement it like basically from scratch, so it's gonna look a bit more messy. So we have this message length, we have the cover length, we do a check if it's too big. We are gonna try to see how big of a message we can put in here, but right now let's just ignore that part. Probably hello from image is small enough, so we don't even need to worry about it. And I guess the next step is to iterate over our message length. So let's see how we can do that. Actually, I guess I'm just gonna do size t bit index. So this is gonna be, well, probably the easiest way. So I was thinking if we iterate over the message length, so for size t I is equal to 0, I is less than message length I plus plus, we are gonna do something like unsigned char message byte. This one is gonna be message at I, so we get a byte different from bit, obviously, and then we can iterate with j over byte size. So j is less than, and then j plus plus. So here we are gonna try to get the message bit. All right, so maybe just as a comment, message bit is gonna be basically us trying to get jth bit from this byte, right? So how can we do that? Well, we can use something called shift, right? Shift left or shift right, depending on how do you want to do that. But let's say, what do we want to do? Let's actually look at how message byte looks like in a memory. So let's say it's gonna be like 0, 1, so it's gonna be 8 numbers, 3, 4, 5, 6, 7, 8. So let's say it looks like something like this. I mean, probably it's gonna be different, but let's just pretend. So first I want my pointer to look at this 0, write it into a byte from the cover. Then I want to move it to the next one, write this one, then this one, this one, this one, and so on until we get to the end. So that's why we need this for loop over byte size, because it's 8 elements. So we need a way to get this item from index j. Right, so how can we do that? Well, it's gonna be message byte, then we need to shift this entire thing to the right, and we need to shift it with so if you think about it, if we want to access this one, we need to shift the entire thing to the right and make it on the first element. I guess that's maybe the easiest way to do it. Although another way would be to build a mask, but no, I mean this one is easier. So we shift this entire thing to the right, and we need to shift it with byte size minus j plus 1. All right, so if index is 0, I want, so I guess it's minus 1. We want to shift, so if j is 0, we want to shift this thing with by 7. So we basically delete all of these values. Then we want to shift this entire thing by 6, and this one is the first one, and so on. Probably you get the idea. So that's how we get the message bit. But how about the cover bit, or I guess cover byte? So the cover byte, let's do unsigned char cover byte. This one is going to be just cover at I, but we actually need another index. So the index is going to be maybe a size t index, and the index is going to be I. So it's going to be similar to how we mentioned here the stride, I think it was called, right? I think it was stride bytes. So we want to go to index I times byte size plus j, right? So if we are trying to write the first byte of the message, we are just going to index by j. But when you go to the second byte of the message, you already need to jump byte size, or I guess 8 elements in the cover image. So that's why we have to create this index. We get the cover byte, and now let's try to write the LSB in the cover byte. So cover byte is going to be cover byte, and we need to clear the LSB, so we can do that with this operation. So this operation will basically set the least significant bit to 0. Okay, and then we want to byte OR this thing with our message bit. So hopefully, hopefully it works. Like I'm gonna be honest. I'm missing a parenthesis. Okay, so this is the cover byte, and then we need to set it back in the cover. So this is the cover byte. Right, so yeah, basically we reset the least significant bit to 0, and then we put some data there. We cannot do it directly because it would overwrite the entire byte. So even if I said this thing is a bit, you cannot have a size 0 or size 1 thing in C. Like the minimum thing, I guess it would still be 8 bits. I mean, you cannot have a 1 bit thing, so it's 1 byte minimum. So this thing would still be like 00001, right? So it would change just this element. So we have to use OR, and because OR is basically addition, if you have something like 0 and 1 is going to be 1, but then if you have 1 and 0, it's still going to be 1. So we have to reset this last bit. And yeah, this one is not, and not 1 is just going to be creating this 11110, right? That's all it does. Okay, so hopefully it makes sense. Let me know if it doesn't, but yeah, this thing just modifies the LSB of the cover byte to contain the message bit that we are trying to figure out. So that's, I guess, gonna write the cover bytes. Okay, let's just leave it like this. We'll see maybe if you notice a problem already. Maybe you noticed it, but let's leave it like this for now, and let's see if we can actually use this thing to hide the data, and then we'll try to retrieve the data. So let's just return 0. Okay, so let's see if the image is gonna look the same. That's my first thing that we're gonna inspect. So let's check out Lena out. I mean, it's pretty much the same thing. Probably it's gonna be changed in the top left, all right? But I mean, to be honest, it kind of is modified, right? It's also the fact that fe does something to it, but hey, it is kind of modified. Can we maybe have like a really big message? I wonder how can we make a bigger message. So maybe I want to read this. So if we take a look, if we do Python 3, 512 times 512 times 3, we can write, and we divide this thing by 8, obviously. So we can write 98,000 bytes, right? I guess we might be able to use DD to create something like this. So let's do, just close that DD. No, I guess man DD is pretty safe to use. I thought it was DD from this destroyer, but maybe it's just me, I don't know. Okay, so I guess we want to create an off file. So we write to a file, and if file is gonna be probably something like device random, right? And we read up to bytes at the time. So default 512, and we need something like input blocks. How do you use this thing? Okay, so we want BS, right? And count. I think that's how you do that. So okay, let's try to use it. So DD, we are gonna use as an input file slash dev slash, wait, was it, I don't remember if DD uses that, but yeah, whatever. Block size, let's say the block size is 512, whatever, and then we have count is equal to, let's do 1 for now. Let's just make sure that this thing works. Yeah, I don't remember if you test.bin. Okay, so you don't, was it without minuses? I don't remember. It's weird. Okay. Okay, yeah. So if we check test bin, we have some data, and it's 512 big, right? So what they say, we want 98. Let's try to divide this thing by 512. 192. Okay, so let's do 192, right? So we have basically the amount that we can hide in this image. It's like exact amount, right? So if we do one more block, it's gonna fail. So how can we now maybe use this thing? Oh, I guess we need aids after all. So let's download this thing, because this library provides you a function to read a file, so that's pretty useful. So let's get this thing, and as I said, it works similarly to how STB image works. So I can do aids implementation stage, and we can just read that thing. So let's say before we do hide lsb, somewhere around here we do aids io read, and we have the file name, it's test.bin, I guess. Yeah, it's test.bin. Then we read into a string slice, so we want to define its string slice. Let's do 0, so we just pass it in here, and the read mode is gonna be read binary, I guess. RB, I think that's how you specify it, and it gives you, I don't really care about the result, let's just pretend that it's gonna work. So we're gonna read this thing. Let's do printf printf message loaded size percentage, I mean it's gonna be lu, but that's something, and let's do len. So I mean it's basically the same as ds.h but with different names and a bit less cluttered. Okay, so we're gonna change it, so let's just make sure that this thing works. Okay, let's run it. So message loaded with this kind of size, perfect. So let's pass here the ss.str and ss.length. So let's see if it's gonna be able to hide. So it's able to hide it. As I said, this thing is barely fitting, but let's see if, so that's kind of annoying. We can see the artifacts though, so maybe there's something wrong with this. Not sure. Honestly, I don't think it is wrong. So because we have the message byte, cover byte, cover byte is equal to cover index. Maybe I could just do something like printf. We can take a look at the value of cover byte and the value of cover byte afterwards, right? So we can see how it's converted. That's something that we can look at. I mean, it's gonna be insanely long, but that doesn't look right, to be honest. I mean, if you add 1 to 74, it shouldn't become 110. It should become like 75. So yeah, it's definitely something wrong here. So we have cover byte. I mean, this thing should just let's do something like this. Let's check if that thing is fine. So yeah, that thing is fine. See, it erases the least significant bit. So from 173 it becomes 172. 74 stays 74 because it doesn't have anything in the LSB, so that looks good. Maybe I did something wrong here. So here we take the message byte, we shift it, and I guess I forgot to end it with 1. So we have to also do an end 1 in here, because or you can even do 0b 00001, like make it look nicer like this, but I mean it's just 1. So I think that was the issue, that I forgot to end it with 1 at the end. Yeah, so now we can see it's 81 and it becomes 80. 185 becomes 184. So if we check out lena.out, it should look exactly kind of the same. I mean, maybe there are some artifacts, but barely noticeable. Maybe if we compare the both images, it's gonna look different, but I mean, it's kind of the same thing. Yo, thank you. I just saw the message. Thank you. Yeah. So that's how we get the cover image modified. Perfect. So let's try to check if we were actually right about the number of blocks that we can write. So let's do 193, and this one should fail and say the data is too big. Nice. So that's actually working. Nice. Yeah, so that's how I was thinking to work with this LSB thingy. That's kind of nice. But the next step that I was thinking about was, what if we try to modify more than just the LSB? What if we try to modify the last 2 bits? Or maybe we can parameterize that, right? And try to modify more than just 1 bit. Obviously, the other thing that we wanted to do was to retrieve the information. So let's do retrieving the information first, because that's kind of more important. So let's do show, and it's gonna use LSB. Here we have it's no longer the cover image, is the data, I guess. So it's the modified image now this time. And what do we want to do? Obviously this one is gonna be const. We don't want to modify it, but now we want to retrieve the message, so we are gonna have that there, and the size is also gonna be a pointer because we are gonna change it. Perfect. And yeah, I mean, let's try to actually do the reverse of this thing. All right, so what are we gonna do here is iterate until data length. And maybe now you actually see the problem is that we don't know when to stop reading the message, right? And yeah, obviously we don't even know if the data contains a message, but that's I mean, we know it contains, but what if you have an image and you're like, oh, does this image contain some LSB data? Well, you use this function, you check. If it doesn't work, it doesn't contain LSB data. So yeah, that's something. Okay, so here we get the message byte. Decoding should be much easier because it's just decoding. So we get the message byte. I guess it doesn't make sense. We don't get a message byte. So we get the index, right, from the data. I guess even then it doesn't make sense. So we are gonna have data byte is gonna be data at index I, and we want to find the least significant bit from here. So that's gonna be, so the data bit is gonna be basically this part. This time I'm not forgetting about the end one, so it's safe. So this is gonna be data byte, and we don't even need this thing. It's just, yeah, we don't even need to shift anything. We just end it with 1, right? And this gives us the LSB. But at the same time, we want to build one of these bytes. So how can we do that easily? I guess the easiest way to do it is to do something like I is equal to, okay, let's just do something like that. Let's iterate with byte size as the step. So then we can use this for j thing, and then we keep using our index. So we do it the same way, right? So just so it looks more similar, right? So we iterate this thing. This time we iterate it by 8, then we have an intermediate for loop. Then we get the index of the data byte. We get the data byte. We easily get the LSB from there. And we want to modify the message now. So to modify the message, I guess another thing we can have is something like size the message index. Let's call it ME. Wait, what? MI. And MI is gonna increase by 1 every time we go through here. So yeah, that's fine, I guess. Okay, so next step would be to do unsigned char message byte. This thing is gonna be message .mi, right? And we want to modify something like this. So we are gonna do, okay, so that's how we get the data bit. And I guess we just want to shift this bit into its position. And or, okay, so it's gonna be message byte, or, and here we are gonna put our data bit, right? We get the LSB, and we have to shift it to the left, right? And we have to shift it to the left by the same amount as before, because it's just, I mean, it doesn't matter this value here, it just needs to be the same, right? So that's the entire point. If you shift to the right with this amount, when you decode you have to shift to the left with the same amount. Okay, hopefully that's gonna work. It's, you know, probably our motto here. I think that should be good enough. All right, so it looks kind of similar, I would say. We get the index of the message, then we get the data byte. Here we were getting the message byte outside of that. And then we basically do the reverse of this thing. All right, so if you think about it, if you do the reverse of it, I guess it looks kind of different, but yeah, hopefully it's is the reverse. Okay, so let's return 0, meaning that it works. And let's do stag show. So here we can stag show LSB. So this one wants the modified data, it wants the length, so cover length, but now it wants a new char pointer. So let's do unsigned char pointer message. Let's make sure it's zeroed, unsigned, or I guess size t message length also 0. So here we pass the message and the address of message length, right? And this should give us back the message. I guess here we can just put the message and the message length, just to make sure that it's unsigned. That's, you know, message that we can actually read. And we can printf retrieved message And let's put here %s and the message. Well, I guess the problem is this thing needs to be, allocated, obviously, because otherwise we get segmentation fault. So, let's just make it into, I guess we can do x times y times component divided by byte size, just to have something. Okay, I'm stupid. I have to malloc. Or I guess I can use calloc because that's gonna make everything 0. And we can just do size of char because that's something I like to have. Wait, what did I do wrong? Oh, calloc also wants the value, so 0. And obviously it's a pointer. Yeah, it doesn't really matter that it's leaked because the program will end. So, Sibas, what the fuck? Well, I mean, we don't need to read this thing anymore, so let's just remove that. Honestly, I never seen this error before. That's interesting. Sigbus misaligned address error. Okay, let's make sure that the decoding works properly. So we are iterating the entire data, right? And I said here that we want to no idea. I mean, do you watch coding stuff or is it just random YouTube working its magic? Yo, hello. Yeah, right now we are trying to debug our LSB decoding, so it's gonna take a while. So here we are iterating over the data length and we are stepping with byte size, right? The main reason is because I want obviously to step by byte size, and then I want another for loop that's gonna fill in the blanks, so go from 0 to byte size. Obviously this is how we compute the index, but maybe it's not because we don't need to multiply with byte size, right? It's just I plus j because we are already multiplying with byte size. So it's just I plus j. That's how we get the current index. Then we get the data byte, message byte. That should work. It's just message byte. Let's just check if it works now. Okay, so as you can see, we get the message, but we also get a bunch of garbage. Curious why it did this. Malloc corrupted top size, whatever, it doesn't matter because like we got the thing, but we also got a bunch of extra garbage, right? So the reason why we got all of that extra garbage is we don't know when to stop, so we iterate the entire data length, right? So we might want a way to include that message length in the image itself. So when we encode our message, we might want to encode the message length before our message, right? So it's like building some kind of TCP protocol where you put the package or like the packet length and then the packet, right? So that's something that we can do to avoid that problem. And I mean, you know, why not? Let's try to do it. So let's try to encode message length in the LSB. And I think we could have some kind of utility function that hides a byte. Yeah, like why not? We could have some kind of function, static void util hide LSB. So how this thing is gonna work is we're gonna have some kind of unsigned char pointer cover that we want to use. Let's say we don't do the cover length. We already know that it's fine, so we don't need a cover length for this one. It's just the pointer where we start. And then we want to hide 1 byte. So it's gonna be an unsigned char and the byte that we are trying to hide. So this is gonna be our helper function, right? So obviously, if we do a for loop starting with 0 and we go byte size, so it's gonna be this inner for loop, right? That's what we are implementing at this point. So byte size I++. I just want to see if it's gonna be a bit different, but I don't think so. So we are just gonna have something like this, right? The index is just gonna be I, so we don't need to do anything about it. The cover byte is just the ith element from the pointer, from the array, and then we just need to copy paste this thing here. So maybe I'm just gonna call it pointer byte. So we have the pointer byte, and then here we just do something like this. We do that, perfect, and then we write back the pointer. Okay, so I think this should be a good util function. And what we can do about this part where we hide the message is just use util hide LSB. The pointer is not gonna be just cover, we have to do some plus on top of it, and I think we want to offset it by I times byte size, right? And the byte is gonna be just message byte. Let's double check that this thing works. Oh, and we don't even want that inner for loop, so we just do this part. If we run this thing, we still have the same message hidden, and I think the Lena image should look the same. I think it's the same, especially in the top. Okay, yeah, fine. All right. So this, I guess it makes it much easier. I mean, we can even just get rid of message byte and just do it like this. So hopefully it makes even more sense now that you look at this thing and you're like, okay, so we are just taking the ith byte and we put it at this address, or I guess starting with this address. And the reason why we do multiply with byte size is because we take 1 byte and we fan out each bit into byte size amount, so it's like multiplied with something. And when we are gonna do into the last 2 LSB is gonna be divided by 2 here, right? So we hide twice as much data, kind of. Okay, so that's a good refactor we did. Makes it much easier. So the next step would be to try and hide this message length. So let's try to do that. So we are gonna do size t I is equal to 0, and how much how much data do we have to hide? Well, it's size of size t. I think it's size t is 8, right? It's unsigned long, so it's 8 bytes. I mean, it's 8 bytes that we are losing, but it's gonna help us with figuring out the length of our hiding protocol. So it's doing that, and then we can just util hide lsb, but this time we need to, I mean, we kind of need to compute the length byte. So unsigned char length byte. Let's say we do something simple, and it's gonna be just converting message length. So we convert it to a pointer, we take the address, we convert it to unsigned char pointer, and then we take the ith element. So it's like this thing is 8 bytes of data. We just interpret it as 8 bytes of data and we index it. So I know it looks really weird, but in C everything is unsigned char pointers. So yeah, I think I covered this topic like a while back. It was like a video on like pointers in C or something. I mean, if you search for it, you'll probably find it because it was kind of doing decent. But yeah, we try to hide that length byte. So now we also have the length hidden in the message. If we run this thing, we should see something about the... I guess we don't see it because I don't know why. Oh, because we are overwriting it. Right. So here when we write our message, when we send the cover as a pointer, we need to add an extra offset, which is size of t. So we need to do plus this thing because we already written in that place of memory. So if we run it now, we don't see that still, but why? I guess it's because we need to multiply it with byte size as well. Right, because here, yeah, we multiply by, yeah, okay. Nice. I guess whatever. Yeah, I mean, show LSB is probably a bit broken, so let's try to fix show LSB. So the first step would be to create some utility that does the same thing as hide, but in reverse. So it's gonna be util show LSB. We get a pointer, and I guess we also get a pointer to a byte, and we are going to try to write into this byte the data from the pointer. So obviously we need to iterate from 0 to byte size because that's how big a byte is. Then pointer byte is just gonna be the first, not really. Yeah, like pointer byte should be this thing. But then, so if we do pointer byte and we shift and we do end1, we get the LSB, so that should still work the same. Okay. And if we do something like byte and we shift by byte size minus I minus 1, this should give us the position. If we OR these two things, I mean, we get the same thing as here, but so if we OR these two things, it's not working right because I also have to shift this value, because this is just the LSB, but this is the position where I want to write that LSB. So I actually have to shift not the byte, but this thing. So it should be something like this. So we have the bit, the LSB bit. I guess that's repetition, but yeah. And we want to shift that least significant bit by this amount. All right, and this should build us something like a mask. So if you think about it, let's say the LSB was 1, it's gonna build something like this, right? If I index was, I don't know, 3, I guess. So it's gonna build this mask, and we need to OR with byte. So OR equals. So I think that's all we need to do to modify the byte. So let's try to use this show LSB in our code. So here so what are we doing? We have I, we have J. Can we rewrite this thing a bit better, maybe? I think that's good enough. So let's take a look here. So if we do util show LSB, we have the pointer, and the data pointer should be data plus I, because we have to write every byte size, every 8 bytes into 1 byte, and the byte where we write should be message plus mi, which is going one at a time. So I think that's actually unsigned SharePoint. Oh, so I mean, yeah, sure, this can be a const. So I'm pretty sure that's all we need to do here, but we added this extra header, so we have to parse the header as well. So something cool that we can do is something like for size t I is equal to 0, I is less than size of size t, I plus plus. We can do the same thing as we did here, but now we don't need to get the address. We can just cast it into that. Let's do plus I instead, so we get pointer to the length byte, and then we pass it in here. So now this, since we are getting a pointer to a byte from message length, it should give us, it should modify it, right? I mean, we could even just pass it like this, so it should work. So though here we don't even need to do something like that. I mean, I think I still want to do the same for loop like here, but instead of size t, I think we have to do, no, I think it was fine. The only thing I have to do is multiply I by byte size, right? Like that's the only thing we need to do. And then we should get a message length back, and this message length we can just printf it lu, and it should be data length. It should show us, oh, it's message length, sorry, message length. It should be the right value. I mean, it should show us that before its segmentation faults. All right, so it's 16, which was the right value, right? This thing was 16 characters. Perfect. So we get the length. And what we could do is allocate the message here, right? So instead of allocating it here, we can allocate it. So we set it to null, we send the address, and now we can just allocate it here. I know it's, you know, allocating memory, but it doesn't really matter. Let's use calloc, and let's do message length. Let's do +1 because I want to add an extra 0, I guess, and initialize everything with 0. Obviously you would, you know, check if it's null or not, but let's not worry about it. Okay, and then similarly to this this for loop, here it's dereferenced. We need to show the LSB from data plus I times byte size, and the message is at index I. But here message needs to be dereferenced first because now it's a double pointer because we want to allocate it. So this should actually write to it, and we already have the 0 byte at the end because we used calloc. So that should actually work now. He said it's gonna work. The received message is empty. That's fine. Okay. Maybe I did something. Let's also show the length with length percentage LU just to have the length. I mean, if the length is 16, then we did something wrong in yeah, so we did something wrong probably in parsing, like here maybe. Okay, so what if I need to put parentheses? Oh, I mean, I did the same thing again, right? Data plus size of size t times byte size. It's the fact that we added the extra header. We need to add an offset when we do the second for loop because we started 0 again. Okay, fair enough. So I guess that was the problem. So hello from image with a length. So we actually now decode this thing properly. It's no longer that extra junk at the end, right? So we know when to stop because we added this length header. Okay, so I mean, that's kind of cool. So as I said, maybe we can try to do hide in 2 LSB, so doubling the capacity of our hiding algorithm. And obviously a cool thing, can I was thinking, how can I easily switch between these two? I guess I'm gonna do something like this. So this is gonna be ss string sslen. So if we run it like this, it's not gonna work because we added the extra header. That's weird. Oh, I guess I forgot to modify my check here. So here we do message length times byte size. We have to do plus size of size t times byte size. So we cannot have, you know, now the header is part of the message. So we need to have something like this. So now it should say that it's too big. Data is too big. Okay, obviously we don't do like error checking, so yeah, like this thing is null. But I wonder why it's not segfault. It's sigbus. Like what? Again, never saw that error before. Okay, anyways, so as you can see now, that file was too big, and before it was the exact sweet spot. So this header removes some, I guess you could say it removes some capacity from our algorithm, but it's only what, like 8 times 8, so 64 bytes. So yeah, it's pretty negligible. Pretty crazy that I was able to say that in such a easy way. Okay, so let's do hide. Should we make it parametric? Int count. Let's do it like arbitrary. So this was hide LSB only 1 byte, but now let's do LSB n, so it's like n bytes. So first of all, we need to assert, we can use assert that count is less than or equal to byte size. So you cannot try to hide a byte in 9 bits, or I guess you know what I mean. You cannot have the count larger than the byte size. That doesn't really make sense. Okay, we basically want it to be 1 or 2. Maybe we want to restrict it to powers of 2 because that's gonna be easier for us. Since we are using this thing, we are gonna know that we are gonna make it 2 or 4, so we can just use division here. All right, so basically the idea is, okay, so let's think about it like this. So we have before we had the count of 1, right? And we had to iterate from 0 to byte size 1 by 1. Now if we increase the count, what I would say is we probably want to iterate not by 1 but by count. So here this would be the first change I would do. I would say, okay, we want to increase I by some count. Okay, that would be the first step. Although maybe we want to do it like byte size divided by count. So we want to do it like this because let's keep I to be the index of the pointer because it's gonna make our lives easier. But it's basically iterating count items at a time instead of only one. Okay, and that basically tells us that instead of fanning out a byte into 8 other bytes, we are fanning it out into 8 divided by something. So if count is 2, we are fanning out 1 byte into 4 other bytes. And you can see why if count is larger than 8, you would do what? Fan out 1 byte into 0.5. That's not gonna work. You cannot fit 1 byte into half of a, well, I mean, if you could do that, that would be cool, but you cannot. So yeah, so the maximum should be 8, and then the image is gonna be like way too changed. So that's what we are gonna benchmark next. See if the image is gonna be way too changed or not. Okay, so we have byte size, we divide it by count, we get a pointer. Here we have to reset, that's going to be interesting. We have to reset not only the least significant bit, but count least significant bits. All right, so let's try to build that mask. So it's going to be unsigned char mask. And how do we build this mask? I guess we need a for loop for it, so let's make it 0. Unsigned size t, j is equal to 0, j is less than count, j plus plus. So we just want the mask to be mask or, and here let's do 1. You know, we can use 0b, 1 2 3 4 5 6 7 8. Is it? Yeah, so you can visualize it better like this, right? So we shift this thing by j, so we just move this one around, right? Initially it's going to be the same thing, we shift by 0, but if count is 2, we are going to have 1 and 1, so we are going to have 2 1s at the beginning, so that's going to be our mask, right? And then we need to build this byte thingy, so maybe we can just do it right here, right? So maybe we can just copy paste this thing and put it here, and maybe to make it better, like visually, let's do it like this. So this thing, hopefully it makes sense, is like the mask. It's 1 here, then it's a 1 here, and so on, based on our count. And then here we have our byte, and we want to shift the byte to the right. And now we have to figure out the amount that we want to do that. So we want to do it, let's say once or twice. So obviously it has to be byte size, that's no question about it. But then the question is, how much do we subtract from byte size? So if it's gonna be the first one, let's say we subtract I think we also have to subtract j somehow. So it's gonna be, let's say we reach the end here, so we get to 4, so we have 8 minus 4 is 4. I guess it's not right. I think it's I times count. We need to do I times count probably, and this is gonna be a number from 0 to 8, right? But I'm pretty sure we have to do something with j, like maybe plus j. Let's just try plus j, why not? Plus j minus 1. We're just trying things until they work, right? Because it's gonna be either plus j or minus j, it's one of the other. So basically the idea is we have this byte size, it's gonna be 8, and then we have I times count, which is gonna be, let's pretend count is 2. So it's gonna be 0, 2, 4, and then 6 and 8. Right, so it's gonna be maybe at some point 8 minus 6, and then j is gonna be 0 or 1. So this is gonna be 8 minus 6 is 2, plus 0 and plus 1, so that's 2 and 3, and then the minus 1 from before. So I think that's fine. Because let's say, I don't know, I is equal to 4, which is the last one. Oh, no, no, no. 3 is gonna be the last one. So this is gonna be 2. Okay, I think it's minus j, because for I is equal to 3, this thing is gonna be 2, then we subtract 1, so that's gonna be 1, and then we subtract 2, so it's gonna be 0. Yeah, I think it's minus j. Okay, anyways, so that's how we build our mask for this pointer byte. And I think we just have to end pointer byte with this mask. So we can just maybe say pointer.I is end equal mask. I think that's just it, probably. And I mean, how we can test if it works is hide LSB. Let's implement hide LSB as util hide LSBn. I mean, I honestly, it's quite, I don't know, in my opinion, this part from C where you do bit arithmetic, it's pretty fun, but it's really hard. Like it's really hard to get used to it. I mean, if you practice a lot, you really get into it. When I was doing the Arduino project, that was pretty easy. Like I got pretty used to it, but now, I mean, come on, like this, if this thing works first try, I'm gonna be impressed, not gonna lie. So let's see if it's, oh, wait, it's assert.h. I don't know what I was smoking. I mean, I tried, but apparently it's not that. Okay, so now we know. Maybe we can do some printf debugging, right? Let's get back this function. Okay. I mean, we could compare and see if it looks kind of similar. So oh, it's end one here. It shouldn't be end one. We should have like this thing should be the same as this thing. And I guess, yeah, no, it's kind of it's not really right. Okay, let's but this part, it's almost right. So we need this instead of 1, right? So this is gonna give us basically this part. That's right, I would assume. But maybe instead of mask, we want the pointer directly. So let's say pointer byte is pointer at I. Right, and now instead of mask, we could do pointer byte. Okay, and I mean, we still need this thing, but I mean, we were pretty close. I mean, it's good that we failed once, because, you know, usually it doesn't work first try, but then it works. Okay, so maybe this is gonna work now. Okay, like it's, nope, I don't like that formatting. Let's do it like this. This looks a bit better. So it's, now it looks more similar, I would say. So we have pointer byte. We want to delete the element from J, and then we want to add there the element from byte, right? So it looks kind of similar, if I'm being honest, but it's also quite different then. Okay, so util header sbn, let's do the byte, and then let's do, oops. And I guess the reason why it was taking so long here to execute was because the header was wrong, so it was trying to read 1 million elements. Okay, let's see. Oh shit, it's not working. But at least we got a length of 0. Oh shit. Okay, so here we are overriding. Okay, yeah, I see the mistake. So here we are overriding this part. So I don't want to overwrite it. I want, let's create a second variable char. Let's keep using mask as our secondary variable. So here when we overwrite, we want to overwrite the pointer, but we don't want to like overwrite our mask. Right, so basically we want to delete this element, the j element, and replace it with the byte. And for that we are just gonna do something like this. But the problem is we still also want to remove that. So if you look here, we remove it from there, but like would be cool if we had something like shift with default value. So instead of 0 we would get a 1, but that's not really how it works. Okay, fair enough. Maybe we want to build the mask separately, so maybe we want to do something like 2 for loops. Fair enough. Let's do 2 for loops. So j goes until count, j plus plus. So in the first for loop we are just deleting the right? And then in the second for loop we are just adding the extra byte. I think that's better. Shit. Pretty confused. Let's do some printf debugging. Printf. So here we are gonna do the pointer byte, and then let's check out the pointer byte at the end. So I would expect the last bit to be deleted. Right, here it is, here it is. So that looks good. And then over here I would expect that it was somehow just modified. Well, what if we just replace count with 1? Is it gonna be the same stuff? Yeah, it kind of is. So right, because this thing would turn into I, this would be 0. Weird. Yeah, like that, that looks good. Oh, what the fuck, why am I doing an and here? Okay, I guess I was doing an and there, so maybe that's the reason. Okay, so it works the same. So I guess I was doing here an and equals, which was wrong, but I'm pretty sure that these two kind of need to be in separate for loops. And if this part was hard, oh my god, let's okay, I'm just kidding. Let's do show lsbn. So show lsbn is gonna work kind of the same with count. So let's divide the count. Let's do the same assert just for the time being. So we have from I to count. Then pointer byte, it's just pointer at I. But now we kind of already know maybe what to do here, or we don't. So let's do a for loop. So it's definitely gonna be a for loop like here with j, and I'm pretty sure it's gonna be just byte, or we might want to replace this thing with this kind of stuff. All right, so we do pointer byte, and we get the bit from index j, and then we shift this entire thing by byte size, and we do I divided by count minus j. Or was it like this? Oh, it's I times count because we divide it here. Okay, so I think, and you can compare it, like if count is 1, then this thing goes away, is the same thing, and here it, yeah, so at least for 1 it should work. And count should be 1. So at least for for a count of 1 it should work, right? And let's check out the out image. It looks the same, so it's all good. But let's now define byte count, and let's replace it byte count and byte count. I'm curious, at least for, let's say, 2. It's here. So if we run it with 1, it works. But what if we run it with 2? Is it still gonna work? Shit. I'm curious how the image looks like. It's the same. Okay, so with 2 it didn't work. Wonder why. So we go from 0 to 4. We get this thing. We go from 0 to 2. So we have 0 and 1. We delete these two bits from the pointer byte. I mean, obviously we can also printf it again, because I feel like printf debugging is really good in situations like this. We don't have to think too much. You just look at the thing and see if it's what you expect it to be. Like, kind of, that's my logic. So here, for instance, if it's an even number, if you remove the last 2 significant bits, you get 108. Right? I mean, it's not really true, but yeah, kind of. 127 becomes 124. That's definitely the last 2 bits, so we remove them. and then it becomes 124. So this kind of looks good. Here as well, we remove the least significant bit and we added 3. So that also looks good. So encoding kind of looks fine, to be honest. Maybe it's a problem with decoding. Yeah, maybe it's a problem with decoding somehow. Nah, not really, because even decoding, it's just the jth one, and we just shift it with this amount, so it's also fine. And I guess the problem, no, it's fine because it's shifting, so it's moving it into the right place. So this gives us a full byte. Let's just go over where we use these functions, because I'm pretty sure it's probably when we hide the length byte count, we go up until this size, so we iterate 8. And here you can see we add byte size. So I would say maybe here we want to divide by byte count, right? Here it's byte count. I guess the reason why is we need less bits for one. So here it's also divided by byte count. Here as well, maybe. So even though we iterate 8 elements, we move them into less space. Okay. So least significant bit divided by byte count. Now if we take a look at this thing, it's still length 0 for some reason. I mean, yeah, it doesn't matter the order of operations. I was like, oh, maybe it does. No, yeah, it doesn't really. But here at least it makes sense that we hide in less by byte count. But at least these numbers look good. So I would say the encoding itself is fine. Yeah, like the encoding itself, it should be fine. So here, if we do this kind of division, it also makes sense that it's done here. But I would say this part right here, it's fine. There's nothing probably wrong in the hide LSBs. Um, hmm. Oh, and what's cool is now we should be able to fit even more stuff, but yeah. So maybe we want to have something like size T, byte size should be like bytes, but I guess I'm not even sure what to call it. Maybe just byte count is byte size divided by byte count. But like now we should be able to fit in more data if we use a different. So if we multiply I with this kind of division, huh? Yeah, I really don't know. Let's put it here as well. So it's here once and here. I mean, it looks kind of the same, so like if byte count was 2, here we would do cover plus I times 4, which is fine. Let's just printf something here. Printf %d. Not sure what to look at. Maybe cover plus I times byte count. But let's print it as a pointer. Yeah, it like it goes from multiples of 4, so that looks good. And we have 1 2 3 4 5 6 7 8, obviously, because it's 8 bytes. What if we show something like the value before and after as a D? Let's put like an arrow. So this would be the before and after, right? So became a 0, a 1. So here I would say we have 0 0. Can we build this number? So we have 0 0 from here. Here we have probably a 1 0, right? Here it's also, I think, 1 0. Does that make sense? I don't think so. Maybe we want to also display the length byte %d, just to see what its value is. So the first one was a 16, then we have all zeros. But if this thing is a 16, then why it's not encoded? Like, sure, this maybe makes sense, right? If we end this thing with 0b 1 2 3 4 5 6 7 8, this I think it is going to be 0, right? If we do 132, it's 0, but 224, it's not. Wait, I'm not looking at the right thing, am I? I need to check out 4 of these. Yeah, I need to check out 4 of these. So it's this one. Can we? I don't think let's just maybe, yeah, let's do 4 loop. It's easier. 4 for size t, j is 0, j less than probably byte count, j plus plus. Let's print f. Actually, let's print f this thing and do plus j. Length byte is like whatever, so we don't really care about it, but let's do a comma space, and then we do the same thing here, but we also add printf arrow. So it modifies from these bytes to these bytes. Right? But it's like 16. Right? So we try to hide 16 into this thing. So this byte is a 16. One 24, 0, 36. I mean, 16 would be right. So one of these bytes, it should contain the data from the 16, but why is it all zeros? That's kind of weird. So here we have the byte, and I said the byte is only used here. Maybe we can have some kind of if statement, so here we can still print the bytes, but it's like if byte is equal to 16, we are gonna print some stuff, because that's also something that makes sense to check. So it's like we kind of know that the thing we are looking after is the 16. Okay, maybe without printing that. So this changes to that. See, it's like after it gets deleted, it's not changing, which is kind of strange. So the byte is 16. This should be 8 minus something times 2 minus j minus 1, and then we end this thing with this value. Maybe I'm curious about this kind of what this value is. Okay, let's put some, I don't know, parentheses around it. So it's 0, 0. That's not quite right. Ah shit, it's because okay, so this thing, yeah, I guess this thing. Wait, why do we have an error? This thing is gonna be something like 0, 0, 0, 1, 2, 4, 8, and 16. But then I think the mask that we were using is not right. Wait. Yeah, I'm also gonna try to use Fourier transform and DCT, but right now we are struggling with making LSB work, so yeah, that's where we are at this point. But probably it's gonna be also interesting to look at fast Fourier transforms, see how we can hide even more data probably than with using the least significant bit. But yeah, now we are trying to hide stuff in the, let's say, the last two significant bits, see if it's gonna look the same. But yeah, it's bit arithmetic, which is so annoying. So we have the byte size. I mean, now I'm struggling to figure out what this thing meant. Okay, so we had the byte, right? And we were trying to shift it to the right with something like byte size minus I times count. So I is gonna be from 0 to that. So multiplied with count is gonna give us a number from 0 to 8, right? Then we subtract j and 1. Yeah, I'm not completely sure. So it's now I'm questioning why I did minus j, to be honest. But I mean, it makes sense why. So we were thinking that here we have a byte size, we subtract something like I times count. So let's say I is gonna be 0, 1, 2, 3, 4. Oh, without 4 because it's too big. But 1, 2, 3, 0, 1, 2, 3. And if it's 3, then we have number 2. Yeah. So we shift to the right by 0 at some point. But we always want to end with just one. So I don't think we want to shift by j here. I think we just want to end with one regardless. Right, I think that's maybe the mistake. So the list here we got a 1, right? And it looks like it's a 1 in the right position because it's like 0, 0. Then we have, so this man means 1, 2, 3, 4. No, 1, 2, 4, 8, 16, 32, 64, and then 128. So I think maybe that was a mistake, that we were ending with something wrong there. So I think we always have to end with 1 regardless of that value. But the problem is, so see, we were shifting by j. I think what we have to do is shift the entire thing by j, not just that. So I think that was the issue here, that we have to shift by j the entire thing. And here, yeah, sure, we shift, we can shift the mask, makes sense. But here I think we had to shift the entire thing. Let's just double check. Oh no, it's I guess it's not shifting by j, but by count minus j. So count minus j minus 1. Shit, it's not. I mean, I tried. So yeah, I mean, I see it as 137, so that's good. Right, because this would be the first. No, this would be the first byte. So it would mean that we have 0, 0, then it means that we have 0, 1, then another 0, 0, then another 0, 0. So in the end, this would mean 16, I would say. So it's kind of fine. Maybe it's something wrong here. So we do pointer byte. Maybe, as I said, it doesn't matter what you put in here. It just has to be the same. So maybe here it's count minus j minus 1. So that's another thing that we can follow. Like when you do encoding and decoding, maybe they have to be matching. Let's see. Oh, pretty close. I mean, we got the length of 16. That's a good step. But the data was gibberish. So let's remove these prints. So I think that was the main issue, that we were shifting the mask instead of shifting the entire thing. And here, I mean, we needed to use the same. I mean, we could probably just say j in here, and here j as well. I would say this should work because it's the same encoding. Nope. Oh yeah, whatever. So I mean, that's fine. We still get the 16, but I wonder why. I wonder why it doesn't look right after we parse it. let's see. So, I mean, this part was fine. Oh, wait. No, that's okay. So byte count. I'm curious how the image looks like. It's like, wait, no, it still looks kind of the same, so that's a good sign. So I times byte count, like this part right here, it's good. Let's check if it still works with length of 1. I'm curious. Yeah, with the length of 1 it does. So we haven't broken anything. Maybe this one needs to be as well with the same kind of uh, like thing. If we are shifting with this amount, maybe we want to also shift the mask with that amount. Maybe, yeah. I guess I forgot about that part. Uh, Still no. Still doesn't want to work, I guess. Yeah, like so initially you would shift it with, so you would make this thing a 0. Then we take the byte, we shift it to the right by, let's pretend again the I is 3. So this would be 8 minus 6 is 2. Okay, so I guess we want to subtract count and add j plus 1, like the reverse of this thing. God damn, still doesn't want to work. Because I was thinking like, okay, this would become 2 when I is 3. So we subtract a 2. Then we add, I mean, this part, yeah, it doesn't matter that much. So it become a 2. Then we subtract j, let's say j was 0. So we subtract 0. And then we also subtract 1. So it would become 1. So it shifts the entire thing by 1. And it takes the first element, and this thing is shifted to the left by 1. So it makes an and it adds that to the pointer byte. And this was also shifted and made 0 there. I mean, this was already, like this one didn't matter to be honest, because we are just trying to make the entire thing 0. So yeah, that was fine. it didn't really matter. So, but here it makes that piece equal to the byte, and then when j becomes 1, it shifts by 0, so it takes the next one and it puts it in the first place, and then it moves to the next thing. So we have these two bits filled in. And when I is 0, for instance, this would be 8 minus 1, 7. So it shifts by 7. Take that thing and the next one, we put them into the pointer byte at index 0, then the next two, the next two, and the next two. So they're kind of in order. I don't see any issues with this. They're kind of in order. Maybe it's something wrong here. So let's take a look at this part. So we have pointer byte. First of all, we have count minus j minus 1. So this would be, when j is 0, this would be 1. So it comes here with a 1. Then it comes here. So we have first one and the second one. So this thing would give us not necessarily the bit. I guess that's the wrong thing. It's not really the bit. The bit would be this, but then we shift it by j. I mean, it doesn't matter what it is, it can be an unsigned char. So if you think about this part, it's moving this one around, right? So it's gonna be here, it's gonna make an end, but then we have to shift it to the right, I guess by j plus 1 or by j. I mean, by this thing, I would say, rather. Because if we moved the one all the way here, then we want to move it back all the way to the start. And then we do bit, and we shift the bit by this amount into the byte. Maybe that was the problem. Yo, that was actually the problem. Okay, I mean, absolute cinema right here. And the image looks the same, but we are using 2 bits. Oh, well, I guess, it's wrong to say that it looks the same because we are just using these bits at the top, so you can't really tell. But if we do the dd command with 192, it should fit without any problem right in the image. So let's see. Let's do this part. Let's comment this one out. And instead of printing the message, maybe we just print the length, because it's gonna be garbage data, right? So this, retrieved message, invalid size for malloc. Wait, it does the same with one. I mean, here is gonna say data is too big. Let's dd something smaller then, just for testing purposes. So like 1. Invalid size. The fuck? And let's still print the message. Oh, what we can do is print a certain length, right? So we can say print 16, just so we don't print a bunch of garbage data. Invalid size, the fuck? I mean, at the end of the execution, we could also free message, just in case. But well, let's use malloc. Let's be real about it. So message at message length is gonna be 0. Yeah, I guess calloc it's stupid. Okay. Whatever. And I mean, at this point, we might be able to just write our message in the file. So we could as well just go into our test bin file and say hello from bin, and it should is this not the right printing? Oh no, we did something wrong. I guess now it only works with one with two LSBs. Wait, it doesn't work. um that's interesting. I mean, malloc your size of unsigned char. Okay. Let's just not put that 0, see what happens. Oh, oh, maybe message length is wrong now. %d message length. Oh, it's %lu, but whatever. Curious what? Yeah, I mean it is 15. So kind of weird. Why did it work with calloc? I mean, when I say it worked, it was seg faulting at the end, but wait, what the fuck? Ah, I have to mem set with 0 or something. Mem set message 0 and then this entire stuff. Yeah, that's why I want to use calloc, but I don't know why it seg faulted there. Message length. Okay, I mean, I'm just gonna use calloc. Let's do a byte count of 1. Huh. If I add that... Okay, now what the fuck? If I add that extra zero at the end, it's not showing the message. But I wonder why. Because it's definite, like it doesn't matter if I do +1 or... Okay, whatever. I mean, I'm just gonna base my stuff on the fact that but yeah, I don't know why. It's I mean, we could just try to add a bunch of stuff like this just to see with length. Hmm. Yeah, that's like an interesting error message. What the fuck? Malloc invalid size unsorted. The end of the allocated memory by 1. Interesting. Fuck. But we don't really... Message plus I till message length, but show LSBN doesn't do anything to byte, so I'm not sure. But I mean, I'd say it's fine that we actually got it working with 2, so that's decent. So yeah, I guess that's gonna be that part for today. Not sure why it doesn't work with bigger ones, but you know, I'll try to figure that one out. So yeah, I guess that's gonna be it for today. So let's check in the next one. So see you.